Okay, so let's review our problem solutions for the practice problems that you just did involving basic mole calculations. Our first problem asked us how many sodium atoms are in 6.00 moles of sodium. Remember, it's always a good idea to ask ourselves what we're converting from and what we're converting to. In this case, we're asked how many atoms, so that's where we're going to. And what we're converting from, therefore, is moles. We want to reference back to the mole from our lesson and remember that there are two main conversion factors that the mole gives us. Converting between moles and atoms, which is Avogadro's number, and converting between moles and grams, which is the molar mass on the periodic table. In this case, it's between moles and atoms, so that means we're going to be using Avogadro's number, where 1 mole, in this case of sodium, equals 6.022 times 10 to the 23rd sodium atoms. And since in this unit we're also remembering that we're learning symbols for the elements, this is one of those you don't want to get confused. The symbol for sodium is not SO. It is Na because it used to be called natrium. Okay, so since we're converting from moles, the problem gives us 6.00 moles to start with. And remember, we want to always write every single unit down. We're multiplying by our conversion factor. Remember, since our unit is moles of sodium, that must go in the denominator to cancel out. We look to our conversion factor for where moles of sodium is, and the number is 1 that goes with it. We know what we're converting to is atoms of sodium, and that means 6.022 times 10 to the 23rd goes on top. Make sure our units cancel. And now we just do our multiplication. We're going to multiply 6.00 times 6.022, which will be roughly 36. Oops, get my black back. 36.132. And of course times 10 to the 23 atoms of Na. Our sig figs here, the least number we can see, is going to be 3 sig figs. And let's convert this to proper scientific notation. Left means larger, increase to 24. So to 3 sig figs, we're going to keep our 1 the same. 3.61 times 10 to the 24 atoms of sodium. And there you go. In our next problem, we're asked how many moles of uranium are in 2.2 times 10 to the 32 uranium atoms. we're converting from are atoms of uranium. And this time we're going to moles. So this is the opposite of what we did last time in problem number 1. Since it's just the opposite, we're using the same conversion factor, just in reverse. 6.022 times 10 to the 23rd atoms of uranium equals 1 mole of uranium. We write out what we're converting. It's our atoms of uranium. That means atoms of uranium must go on the bottom in the denominator and moles on top. 1 mole to 6.022 times 10 to the 23rd. Whoops. I made a mistake here, and I think you may have caught it. We can see that it's actually to the 32 for our uranium atoms. We should always be checking ourselves as we're doing these problems, making sure that we're doing everything right. Make sure our units cancel out, so we've set everything up properly. And now we do our math. 2.2 divided by 6.022. Gives us 0.365327. We're doing division with scientific notation. That means we're going to subtract our exponents. 32 minus 23. And that's going to give us 9. We're going to have 2 sig figs in our final answer. And we want to put this into proper scientific notation. Reduce it to 8. That 6 is going to round up. We've got a 5, we got to be careful, but we have non-zero digits next to it, so we know it's going to round up. 3.7 times 10 to the 8 moles of uranium. And there we have our atoms to moles conversion problem. Our third problem. In this case, we're asked about what the mass is of 5.00 moles of carbon. You'll see I have my periodic table out because, well, when we're dealing with mass, that must mean we're using the conversion factor of molar mass. Always keep the same strategy down. What am I going from? In this case, it's moles. What am I going to? It's mass in grams. And as we've already identified, that mole conversion is going to be the molar mass, which is grams per 1 mole. So 1 mole of carbon equals, and I already know what it is because as an organic chemist, you memorize these things, 12.01114. Well, this one only goes to this many sig figs, so it's just going to stop there. grams of carbon. 12.0111 grams of carbon for every 1 mole of carbon. Now, we do our conversion. 5.00 moles carbon times our conversion factor. We know moles of carbon must go on the bottom so that the units cancel out. We know the 1 goes with our moles, which means this must go on top. Grams, and that's what we want to convert to anyway, right? Grams of carbon. 12.0111. Assure ourselves that our units cancel, which they do. Do our math. 5 times 12.0111. We get 60. And go back to black. 60.0555. And that's grams of carbon. Since this is a reasonable number and we're not using scientific notation, we'll leave it in expanded notation, but we do need to change our sig figs. Looks like we have 3 sig figs. We look to the right, got a 5, be careful, but we have non-zero digits, so we round up. So our final answer is 60.1 grams of carbon. And there we have our mole to gram carbon, or mole to gram problem solved. Let's look at our final problem, which is actually 2 problems in 1. Again, you'll see our periodic table out. Here, we're asked about the mass in grams of 2 different quantities of sodium atoms. So, the setup for both of these is going to be the same. We'll be doing 2 problems that are set up identically using 2 different quantities. So, let's ask ourselves what we're going from. That would be sodium atoms. And we're going to grams. Well, we're going to be needing our molar mass, which is 22 point, this one's got a lot of sig figs on it, 22.98977. And that's grams of sodium equal to 1 mole of sodium. I'll just shove that guy out of the way. Now that we have our conversion factor, it's just a matter of doing our dimensional analysis. And I'm just going to set them up in parallel since they're the same problem, really. 12.044 times 10 to the 23 sodium atoms. And here it's 15.0 times 10 to the 23 sodium atoms. Sodium atoms is what we're starting with. It's in the numerator, so it must go in the denominator to cancel out. Now, I've done it this way to show you guys that sometimes when we're doing problems, we set ourselves up and we catch ourselves in a mistake. So what I've done is I've made a typical mistake. I missed a step in my problem-solving strategy. And that's why we do dimensional analysis the way we do. Is we solve problems using steps that we've practiced over and over again. And so what I've done here is I've followed through with my strategy like I should. I've said, okay, I know that I start with what I'm converting, which is atoms, and I must go in the denominator. And so I have atoms, and I look to the conversion factor that I wrote down, and I don't see atoms. And I've recognized that I missed the fact that I don't have one conversion factor that I need to get myself from atoms all the way to grams. So I go back to my original plan and add my missing step. One of the greatest challenges of chemistry is the problem-solving process. And we build in a lot of what we call fail-safes to make sure that as we're doing the problem, we're always building in steps along the way that allow us to check ourselves so that we catch mistakes and we fix them as they arise. So I had my one conversion factor already because I noticed immediately I had grams. And we'll need that conversion factor. But what I missed was my need to go between atoms and moles, which is Avogadro's number. So I'm going to move this over and write in the conversion factor that is missing, that bridges the gap I need to be successful. And that is that 6.022 times 10 to the 23rd atoms of sodium equal that 1 mole. Now I can complete my problem. Atoms of sodium can now be associated with Avogadro's number. Which is equivalent to 1 mole of sodium, which will go on top. So we're done with that conversion factor. Those units will now cancel, like we intended. Now I need to get myself all the way to grams. And that's where I can use the conversion factor I originally wrote. I know that moles must now go on bottom. Where 1 mole equals my molar mass. Now my moles of sodium will cancel out, and I can solve my 2 problems. Let's do our math. Part A is 12.044 divided by 6.022 times 22.98977. That part of the math gives me 4 5.97954. I need to deal with my exponents, and they're easy because I've got 23 in the numerator and a 23 in the denominator, which, since we're subtracting, they cancel. Let's finish this one off. Let's count sig figs. I've got 4, 5, and a lot more. So we're going to go with 4. 1, 2, 3, 4. 7 will round up to an 8. We're going to leave this in expanded notation. This will be 45.98 grams. I left off my sodium here, which I shouldn't have done. Grams of sodium. And I also should have canceled out my units. All the way through. Alright, let's do our bottom problem. 15 times 22.98977 divided by 6.022 leaves me with 57.26 446. Again, I left off my sodium here. Shouldn't do that. And again, 23rd. Those cancel. Isn't that nice? So we can leave this in expanded notation. Look at sig figs. Looks like I got 3 here and 4 here, so 3 sig figs. 2 is going to round up to a 3. I'm going to have 57.3 grams of sodium. And there we have a multi-step conversion, which is very common. In this case, going from atoms to grams, but we could have just as well gone from grams to atoms. We'll see all sorts of different combinations of these conversions in our class. We'll utilize all of them many times in the future. So practice, 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 as I always say, and we'll get our strategies down, and we'll get better and better at these until they become second nature, especially with the sig figs, making sure we get the most accurate and precise answer as possible.